I remember that I owe you a formal proof, and I will do it eventually, but I prepare a kind of a helping trick to make it easier. Okay, so I want to, what we were talking about last time is the notion of formal proofs. Formal proofs in propositional logic. And the idea is that a formal proof is a construction sequence. So we started with saying that the set of formal theorems is, let's call it, I don't know, T or TH, for not to confuse it with true. Theorems is I of the set of axioms that we've seen, and one rule, which is the modus ponens rule. And the formal proof is a construction sequence for this structure. And finally, so we have the notion of what is a formal theorem, what is a formal proof, and finally we have a notation. We use this notation tilted T alpha to denote that alpha is a formal theorem. So these were the basic definitions that we had last time. And on top of it, I gave you the list of axioms, the modus ponens rules, and I showed you some examples of how do formal proof look like. So we showed that for all alpha, for any alpha, this is a formal theorem. Alpha equals alpha. Right? And then we went on to show the soundness theorem. So what is the soundness theorem? The soundness theorem says that any formal theorem is a tautology. Okay? And the way, if, oh, okay, I don't know, does it make a difference if I write any or every? It doesn't, right? Okay. But so if I have a statement saying every formal theorem is something, and formal theorems were defined as an inductive set, then the natural way to prove something for each of them is by induction on this structure. And that's what we did. So the basic step was showing that the axioms are tautologies. And the induction step was to show that if the inputs for modus ponens are tautologies, then the output is a tautology as well. So whenever we have a statement saying every member of some set defined inductively has some property, the natural approach is to try to prove it by generalized induction on this structure. So this is as far as we got last time. Now, we started by listing three desirable properties from proof systems. We said the proof system should, first of all, we have to make sure that everything we prove is indeed correct, and that's what we took care of here. We also want to make sure that there is a way to check what is a proof and what is not. And here there is a way to check what is a proof or not, or what is not, because a proof is a construction sequence in this system. So we just have to go along the sequence, alpha 1, alpha 2, alpha 3, and so on, and check that each of them is either an axiom or follows from previous ones by modus ponens, which is easy to check. It's even easier to check than to check truth with the truth table. So we are still missing the third property, and the third property is the completeness that states that every correct statement can be proven. But we will do it a bit later. What I want to do now is extend this notion of formal proofs to something very natural, and this is proofs from assumptions. So let sigma be a set of formulas and now the set of formal theorems under the assumptions sigma is defined very similar to what we had there. So let's call it theorems of sigma. And this is I of, but now I allow myself on top of the axioms to add the member of sigma. So now, if I want to prove based on sigma, I allow myself to use the elements of sigma as elements in my proof. And again, a formal proof for sigma will be a construction sequence for such a membership. So, namely, alpha 1 up to alpha n is a formal proof under sigma if each alpha I is either an axiom or a member of sigma, and this is the new part, or follows from some alpha j, alpha k, where j and k are less than I, using MP. So it's the same definition as we had before for a proof. The only difference is that now I allow myself to use members of sigma as part of the proof. So let me show you the first simple example of such a proof. Things now look, the first examples are very simple. So let us look at some examples. So let sigma be A and A arrows B. So then I claim that based on these assumptions from A and A arrows B, I can prove B. Can anybody show me the formal proof of B? Yes? Right, I can use A because it's member of sigma. then I can use A arrow B because it is also a member of sigma. And then what do? Then I use modus ponens on these two, and I get B. So that was a very easy one. So let's do a slightly more difficult one. Another example. So now I want to claim that another example. For every alpha and beta, alpha and not alpha can prove beta. Which is, we've already seen it, but we've seen it in the context of semantics, now in the context of syntax. From a contradiction, we can prove anything. If I have both alpha and not alpha, then I can prove beta no matter what beta is. Again, I'm going to show you a formal proof. So here is my formal proof. So I will start with the sequence not alpha, arrows, not beta, arrows, not alpha. Why can I write this sequence? Why can I start my proof with this? Which axiom? First one, right. This is axiom 1. Yeah, you should by now start remembering what the axioms look like. So I have here some A, arrows B, arrows A. So this is axiom 1. Now I will write here not alpha. Why am I allowed to have not alpha as the next line in my formal proof? Yes?
Member of sigma?
Right. It is a member of sigma. Okay. Now you should already be able to guess what will come next. So, what do you think should come next? Yes?
Not beta implies not alpha.
Right. How will we do it? Modus ponens. Right. So now that we have an implication and the head of the implication, we can use modus ponens. So applying modus ponens by applying modus ponens, we can now delete the head and get not beta, arrows, not alpha. But I'm trying to get to beta. So what will I do now? I will write the following. If not beta, arrows not alpha, then alpha arrows beta. Why am I allowed to write this? Right, this is axiom 3. And what have I gained from this now? I can use modus ponens again. Now I'm happy because I can use modus ponens again. So I use modus ponens, and I get alpha arrows beta. But I wanted to prove beta. So how shall we conclude our proof? Now I'll write alpha. And this is allowed because it is member of sigma. And now I'll use modus ponens again, and I'll get beta. So we showed that our formal proof system enjoys this nice property that from a contradiction we can prove anything. Okay, so we've seen two examples. Somehow it feels that proofs from assumptions seem easier than, I mean, if we take the right assumptions. So let us describe some general properties of proofs from assumptions. So some properties of proofs from assumptions. Maybe the first thing to note is that we can extend the soundness theorem. So the first will be extended soundness theorem. So what is the extended soundness theorem? I claim that for every sigma and alpha, if sigma formally proves alpha, then sigma logically implies alpha. Why is it an extension of the soundness theorem? How do I get, assume I prove this, how do I get to the soundness theorem that we saw last time? Yes?
An empty sigma is going to say that.
Right. I'll take an empty sigma, so here I'll get just alpha is provable, and here I'll get alpha follows logically from anything, which means alpha is a tautology. So substituting sigma as empty set yields the basic soundness theorem that we saw last time. That if alpha is provable, then alpha is a tautology. Now, what do you think of how do you suggest to approach the proof of this extended soundness? Whenever I ask you how should we prove it, the best bet is to say by generalized induction. Because I can replace, if sigma proves alpha, I can replace it. Just notice that we can rephrase this theorem as for any alpha in I of axioms union sigma MP, sigma logically implies alpha. And once I rephrase it like this, it is very clear that the natural approach is a generalized induction. And it's going to be very similar to the proofs that we did last time of the usual soundness. The only difference is that earlier we only had one base case, an axiom. Now I have two types of base cases. Either it is an axiom or it is a member of sigma. So I leave the proof to the assignment. But it's basically the same proof that we've seen. Are there any questions so far? Okay, so this is a very important property of proofs from assumptions, that if we prove something from assumption sigma, we know that whenever sigma will be true, for every assignment that makes sigma true, alpha will also be true. And again, this is a connection between syntax and semantics. Because notice that this is a syntactic notion, and this is a semantic notion. This talks about sequences of formal proofs, just checking characters one by one. This talks about truth assignments. Every truth assignment that makes all of those true will also make this true. So we have here another connection between the syntax and the semantics. So let me move on to other properties of proofs from assumptions. The next property looks very, very obvious, but it is not as innocent as it looks. So the next property, yes?
When we're trying to prove this theorem now, and we are trying to do the inductive state, in the inductive state we say alpha is like maybe not x or x and y. So how are we going to...
No. That's a very good point. When you do the inductive step, when you have a structure IAP, you do the induction on the operation P. So the operation modus ponens here is alpha, and alpha arrows beta yields beta. So the induction step will be on this operation, which means assume that alpha is implied by sigma, assume that alpha arrows beta is implied by sigma, and now show that beta is implied by sigma. I'm not constructing, it's not the structure that constructs all formulas, because it's not a claim about all formulas. It's only a claim about the formulas that can be proven from the assumptions. So I have to do the induction step on the operation that is in my structure. Okay? That's an important point. Whenever you do induction, generalized induction, you have to check how was your structure defined. The induction step is on the base case is on the basis of your inductive set, and your induction step is on the operations here. Okay? Good. So the next property is called monotonicity. And monotonicity says that for every sigma, sigma prime, and alpha, if sigma can prove alpha and sigma is a subset of sigma prime, then sigma prime can also prove alpha. So we've seen a similar property semantically, but now it is talking about the syntax, about formal proofs. So why is it called monotonicity? We can rewrite it, in other words, sigma subset of sigma prime implies that the theorems of sigma are subsets of the formal theorems that you can derive from sigma prime. So this looks like monotonicity. If I have inclusion here, I have inclusion of the consequences. And this looks like a very natural thing. If you make more assumptions, then you can prove more things. So why do I say that it's not trivial? Because, curiously, this is not the way we reason in human reasoning. So the funny thing is that, just note, this is just in brackets, note that human reasoning does not enjoy this property, which may sound strange at first look. How come if we make more assumptions, we will not get more conclusions, right? So here is an example why human reasoning is not like this. Assume that your assumptions is everything that's written on Quest. So this is everything, every information you can find on Quest is your assumptions. So you go to Quest and you see that there is going to be a logic class on Thursday at 2:30. So you conclude from Quest, so you have Quest, and you conclude, this is like human reasoning. Human reasoning, there will be a class on Thursday. But now I will add more information. Assume that on top of Quest, you also see on Piazza that Shai is sick. You have an announcement, I'm sick. Now you have more assumptions. But now suddenly, you will not conclude that there is a class on Thursday. So you got more assumptions, but one of the conclusions that you had before suddenly disappeared. And this poses a real problem to AI. When we want to have artificial agents that are able to reason like humans, we don't know how to formalize it. It is still a challenge.
Isn't it just probability, though? So, like, Quest shows that you have a 95% probability of having a class on a given day, but then the probability of having a class on a given day, given Quest and given Piazza saying you're sick, is different. It's just the probability is not.
Right. So, I mean, it's a very good approach to try to talk about probabilistic reasoning and to say that we're not making foolproof conclusions, but we only take probabilistic conclusions. But then when we try to do this, we run into other issues. So I will not get into, maybe if we have time at the end of the course, I'll talk a little bit about this type of probabilistic reasoning. That you don't conclude something with certainty, you only conclude it with certain probability, and we can try to formalize it. But it turns out that we don't have a good modeling for the way humans reason, which is a pity, because you want to have a Google car that makes conclusions on the road the way a human driver will do it, and we don't really know how to program it, because we don't fully understand it. Anyway, that was just a side comment. This very obvious property of monotonicity is not completely obvious. Yes?
I'm curious about what will computer conclude based on the second assumption, or the two assumptions together?
Yeah, it depends on
Conclude anything.
No, it will conclude everything, because now you get a contradiction and you can conclude everything.
Oh.
So from these two assumptions together, he can conclude that tomorrow will never come. I don't know.
Or more accurately, it depends on what you program the computer to do.
Right.
If you try and put that into Excel, nothing will happen.
If I try to put anything into Excel, even your marks, nothing happens. Okay, so let us prove it. The property is very easy to prove. So the idea is that since sigma proves alpha, we want to show that if sigma proves alpha and sigma prime is bigger, then sigma prime can also prove alpha. There is a construction sequence, or if you want, formal proof of alpha based on sigma union axioms. So we have this alpha 1 up to alpha n, and alpha n is alpha. But now, each alpha I is either an axiom or alpha I is a member of sigma, but in this case, in that case, alpha I is also a member of sigma prime, because sigma prime is a superset of sigma, or alpha I is the outcome of MP on earlier alpha j, alpha k. But now if I read this, this just means, therefore, alpha 1 up to alpha n is also a proof from sigma prime. The same proof satisfies the requirements to be a proof based on sigma prime. Yes?
Well, based on this proof, then we can't really say that human reasoning does not enjoy that property because it depends on how we think of human proof. Because still looking at this,
I'm not talking about human proof. I'm talking about reasoning, like the way we draw conclusions. The way, I mean, I gave you a counter example, right? If you just see it on Quest, you will draw the conclusion that there will be a class on Thursday. And with more assumptions, you will not draw this conclusion.
well, also this guy, if you give him more assumption that alpha is not true inside E prime, inside the
If I tell it alpha is not true, then yeah, now it will be a contradiction, and you will be able to prove everything. But no, it's not the same thing, because from having Quest and me being sick, you don't conclude that the moon is made of cheese. You see, here the formal logic will say, sure, now I get the contradiction, now I can conclude everything. But that's not the way we do reasoning. Okay, and we can extend this property a little bit more. We can get something even stronger, which is, so a strong monotonicity and strong monotonicity says the following, that if for every alpha in sigma prime, sigma proves alpha, then the same conclusions. The theorems of sigma are subset of the theorems of sigma prime. So what is the difference? Rather, should I change the role of sigma and sigma? Okay. Yeah. Then the theorem of sigma prime is a subset of the theorems of sigma, and I get a bonus point. What? That's okay. What I'm saying is sigma is stronger than sigma prime. In what sense it is stronger? Sigma is stronger than sigma prime. It's the opposite of what we had there. Sigma is stronger than sigma prime. Sigma can prove everything that is in sigma prime. It's a stronger set of assumptions. Then the conclusions from sigma will be more than the conclusion of sigma prime. So to conclude that, we have to replace the role of sigma and sigma prime. Okay, so, and again, I mean, we are moving a little bit slower than what I expected, so I will not, I think I will leave this proof also to the assignment. I mean, you see, now we cannot repeat the proof that we had here. Because if I have a proof from sigma prime, it's not necessarily a proof of sigma. Right? So, for example, just to see an example, to make it a little bit more clear, let sigma be A and A arrows B, and sigma prime be just B. Then we are in the situation that for every member of sigma prime, I can prove it from sigma. But clearly, this sigma prime is not a subset of sigma. It is not covered by this simple monotonicity. I just claim that anything that I can prove from sigma prime, I can also prove from sigma. How will I do it? If I want to prove something from sigma prime, I need B as an assumption. So I will first use this to conclude B, and then I'll keep going. You see? But I don't have inclusion here. So it's a different statement than the statement here, there. If I have inclusion, then in particular, I'm in this situation. Right? So in this case, we know we can denote it by sigma proves everything in sigma prime. So this is some kind of abuse of notation. Stands for every alpha in sigma prime has a proof under sigma. So this is a kind of abuse of notation because I use this proof sign between sets instead of a set and a formula. And the theorem says this implies that the conclusions that let's write it like this, that the theorems that I can draw from the set B are a subset of the theorems that I can draw from the set A and A arrows B. So sigma here is stronger than sigma prime, not by inclusion, but by being able to prove everything in sigma prime. You look at me like in a very skeptical. No. It's okay? I mean, it also can be your way of fighting falling asleep or something. Yeah. Okay. Let us do some more interesting property. And I also owe you a formal proof from last time. So I need this more interesting property in order to be able to do this formal proof. So the more interesting property is called, or are there any questions about what's there? Okay? So the more interesting property is called the deduction theorem. And just note, all of those theorems that have names, the reason they have names is that those results are, we see them in every logic that we are developing. So if it was just for the purpose of positional calculus, we would not bother to give them big names. But we just demonstrate how logic works. And we'll have the same theorems in every logic that we'll be working with. Okay, so what's the deduction theorem? It says that for every sigma and alpha and beta, sigma union alpha can prove beta if and only if sigma can prove that alpha arrows beta. So if from it somehow tells me about the connection between proofs and the arrow symbol. If based on the assumption alpha I can prove beta, then I can prove that alpha arrows beta. Right? In particular, alpha, from assumptions alpha I can prove beta if and only if I can prove without assumptions that alpha arrows beta. This is just the case that sigma is empty. If from assumptions alpha I can prove beta, it's the same thing as saying that I can prove without any assumptions that alpha arrows beta. Now, before I get to the proof, I just want to motivate you to look at the proof. So let me show you why is it useful to have such a theorem. So before we prove it, let us look at an example of how it makes our lives nicer, easier to get general proofs. So let us prove the following claim, that for every alpha, beta, gamma, if I have alpha arrows beta and beta arrows gamma, from these two assumptions, I can prove the formula alpha arrows gamma. So this is a very natural thing we would like to have in our proof system. If I assume that alpha implies beta, and I assume that beta implies gamma, I can conclude that alpha implies gamma. Now, to write a formal proof of this without a deduction theorem is the kind of things that if I'll try to do now, I will get lost and embarrassed and everything. But with the deduction theorem, it's simple enough that I can do it. So how do we use here the deduction theorem? So the proof, applying deduction, it suffices to show, okay, maybe you can tell me, how can I here apply deduction to make my life easier? The deduction tells me that there is equivalence between proving an error statement and pulling the head of it into the assumptions and proving the tail. So what will suffice to show here? It will suffice to show that from alpha arrows beta, beta arrows gamma, which is my old sigma, but now I pulled alpha in, I can prove beta. Because the deduction theorem tells you if you want to prove an implication, you can pull the head into the assumptions. And that's going to be the same. Yes?
There should be a gamma on the right-hand side.
This should be
On the right-hand side?
alpha arrows beta. This would be gamma. Right. Right, so that's exactly what the deduction tells me. I can pull the head into the assumptions. But now the proof becomes trivial suddenly. Can anybody show me how to do the proof now? Just think about it. Now we have all kind of tools to play with. Yes?
Since now we have alpha, we can use modus ponens to show that beta is true.
Right, so how will I do it formally? What will be my first line?
Showing alpha.
Alpha, because it's assumption. Then what I will write?
Alpha plus beta.
Alpha arrows beta This is again assumption.
And modus ponens applied.
Then I'll do modus ponens and I'll get beta.
And
And then I'll keep unraveling it further. Then I'll get beta arrows gamma, which is assumption. Then I'll get modus ponens again and get my gamma. So this is a very useful tool, this deduction theorem, because it makes my proofs much easier. But there is a cost to pay. We want to use it, we have to prove it. So let us prove it. So now I want to do proof of the deduction theorem. So the deduction theorem is if and only if, and whenever we have if and only if statement, we need to prove two directions. So one direction is very easy. What is the easy direction? The easy direction assume that sigma can prove alpha arrows beta. So therefore, by monotonicity, sigma union alpha can also prove alpha arrows beta. Because I only added more strengths to sigma. I extended it. It's bigger now. Now, by strong monotonicity, it suffices to show that sigma prime, which is sigma union alpha arrows beta, can prove beta. Because my sigma prime, everything in sigma prime can be proven from sigma. Because I know, you see, everything from sigma prime can be proven from this. Because this is already there, this is already there, and this also can be proven from this for my assumption. So if I look at, if this is my sigma prime, then sigma is stronger than sigma prime. So if I show that I can prove beta from sigma prime, I showed it from sigma. But how do I prove beta from sigma prime? That's trivial, modus ponens. I just write alpha arrows beta. Beta is a proof from sigma prime. Because this is an assumption, that's a modus ponens. So we did one direction of the deduction theorem. Okay, so now let's do the more difficult direction, the harder direction. What do we need to show? We need to show that if sigma can prove alpha arrows beta, which direction am I? I need to assume this, right? Right. So I need to show that, show that if sigma union alpha can prove beta, then sigma can prove alpha arrows beta. Now, what I would like to use is what? I would like to use induction, but it doesn't look like induction. So I have to rewrite it as something that looks like calling for induction. So we can rephrase it this statement as for all beta in theorems of sigma union alpha, sigma can prove alpha arrows beta. Now this is the same thing. If I say if sigma can prove beta, it's the same thing for every beta that can be proven from sigma union alpha. The advantage is that this is an inductive set. So now I can use generalized induction on all of those betas. So now we can do proof. Now, prove by generalized induction on this structure. On the structure, the formal theorems of sigma union alpha. Or in other words, this is I of my basis is the axioms. I can use sigma, I can use alpha, and as a deduction rule, I have modus ponens. So I want to do induction on this structure, and I want to show that for every beta in this structure, one can prove that alpha arrows it. Okay, so now we have to just be careful about what is generalized induction. So what is going to be my base case? If beta is, right, I want to show for every beta in this structure, the base case is beta is in the core set. And there are several cases. Beta in the core set, what can it be? Axiom. So case 1, beta is an axiom. What will I do? I need to show that I can prove from sigma union alpha that alpha arrows beta. So here is my formal proof. I will write beta. Why can I write beta in a formal proof? It's an axiom. Then I will write beta arrows, alpha arrows beta. Why can I write this? What? This is axiom 1. Now I will use modus ponens, and I will get alpha errors beta. That's what I wanted to show. I wanted to show that I can prove from sigma, I can prove alpha errors beta. So here's my formal proof of our alpha errors beta. As a matter of fact, I didn't even use any assumption from sigma. But it's a legal formal proof. Okay, so that was the first case. The first case in the base of the induction. So we checked the case that beta comes from here. What else could be in the core? What's the other case? Right. The other case, case 2, beta is in sigma. What will we do in this case? Exactly the same proof, except that I'll write beta, but now it's an assumption. Then I'll write beta errors, alpha errors beta, which is axiom 1. Then I'll do modus ponens, and I'll get alpha errors beta. Just remember all the time what we need to do. We need all the time to show that sigma can prove alpha errors beta. So this is a proof from sigma because I used an assumption from sigma. It's a proof from sigma. That's what I need all the time to show. That sigma can prove alpha errors beta. So what am I left with? Still in the base case. What are we still missing? Beta is alpha. So now we covered the case that it came from here. We covered the case that it came from here. But beta could come from here. So the last case is beta equals alpha. Case 3, beta equals alpha. And I need to show that sigma proves alpha errors beta. So how do I know that? So sigma proves alpha errors beta is, in fact, sigma proves alpha errors alpha, because beta is alpha. And how do I know that? What? We proved it. It's not an axiom, but we already showed, that the empty set proves alpha errors alpha, and now we can use monotonicity. Sigma is bigger than the empty set, so everything that I could prove from the empty set, I can prove from sigma. So see, this logic is just a game. I mean, the only problem with this game is that each time I'm dumping new rules of the game on you, and then I'm playing with my rules before you had time to absorb the new rules. But we just have some rules, and we are playing a game with these rules. Okay, so did we finish the theorem? No, we just did the base case. Now we need to do the induction step. So the induction step is, we assume, here we have to be careful about phrasing the induction steps. We assume that the conclusions hold for the inputs of modus ponens. We have to show that it holds for the outputs of modus ponens. Right? So we have the operation that I have to take care of is modus ponens. But I will not use alpha and beta because alpha and beta are pretty loaded here. So let's use gamma and delta. So modus ponens is I have gamma and I have gamma errors delta, and I want to conclude delta. This is my modus ponens. So now we may have to assume that what we wanted to prove holds for the inputs and should show it for the output, right? So we assume, what do we need to show? So we have to assume that sigma can prove alpha errors gamma, and sigma can prove alpha arrows, gamma arrows delta. And we need to show, what do we need to show? Because the claim, we are doing induction on beta. So the claim is sigma can prove that alpha implies me. So I assume sigma proves that alpha implies me, I assume it for gamma. Sigma proves that alpha implies me, I assume it for gamma arrows delta. So now what I need to show, sigma proves that alpha implies me for whom? For delta. So I need to show that sigma can prove alpha arrows delta. What? All the time, you're doing induction on this guy. The guy that runs in the induction is this guy. So this guy was already shown that I can substitute gamma here. And I've already shown that I can assume that I can substitute gamma arrow delta here. Now I imply modus ponens, and I have to show that I can substitute delta here. Substitute each of them for beta. So I need to show that sigma can prove alpha arrows delta. Okay? Now, the whole difficulty here is just to realize what we need to prove. What do we assume and what do we need to prove? And the main thing is that the induction assumption is about this beta. We have to substitute for beta the ingredients of the modus ponens. So once we realize that, life is easy. How are we going to do it? Does anybody see how we are going to do it? So we assume that sigma can prove this guy. And I mean, really, the difficulty is just in realizing what exactly do we need to show. So sigma can prove the first guy, and sigma prove the second guy. Therefore, by generalizing that, by the strong monotonicity, so by our assumptions, the plus strong monotonicity imply that it suffices to show. What do we need to show? Now I can strengthen sigma because sigma can prove all of those guys. That sigma augmented with alpha arrows gamma and alpha arrows gamma arrows delta can prove alpha arrows delta. I wanted to show that sigma can prove it. But since I assume that sigma can prove these guys, everything that the big set can do, sigma can do. That's a strong monotonicity. Sigma is as strong as all of those guys because it can prove this guy and can prove this guy and can prove everything in sigma. And now this is just an application of one of our axioms. Which axiom do you think will become handy here? Axiom 2. I will write here alpha arrows, gamma arrows delta, arrows that alpha arrows gamma, arrows alpha arrows delta. This is just axiom 2. And now I will write alpha arrows, gamma arrows delta, This is assumption. Then I'll do modus ponens, and I will get alpha arrows gamma arrows alpha arrows delta. Then I'll do alpha arrows gamma assumption, and do modus ponens, and get, now all I need to do is alpha arrows delta by MP. So we finished our proof of the deduction theorem. And I mean, I can understand that it's a bit kind of confusing, but it's just a matter of getting used to the axioms and the rules of the games. Nothing here is too demanding intellectually. It's just getting used to the new game. Now let's see if I got used to the new game. Let me try to attack again the formal statement that I got stuck on last time. So here is another example of the use of the deduction theorem. Now it's gone. Now I have a tool that can help me. I wanted to prove, so we have this claim that for every alpha, we can prove the double negation alpha arrows alpha. You remember that's what I was trying to do last time and got stuck. Now, in the proof, I'm going to use the deduction theorem. So in the proof, I say by the deduction theorem, it suffices to show that what? Yes?
That assuming not A, we can prove A.
Right. That assuming not alpha, I can prove alpha. Okay. So now here is the formal proof. Here is the formal proof. Hopefully. So what I will do is I will write not alpha arrows 1, 2, 3, 4 alpha arrows 1, 2 alpha. Why can't I write this? This is just axiom 1. Right? This is sum A. This is sum B. This is A again. Now, what can I do with my assumption? I will write not alpha. This is an assumption. And what can I do now? I can do modus ponens. I can apply modus ponens. And I got to 1, 2, 3, 4, 5, 4 alpha implies 1, 2 alpha. Now, I'm going to apply. So far, are you with me? We are playing by the rules. Now I'll apply, you'll tell me which axiom it is. 1, 2, 3, 4 alpha arrows 1, 2 alpha arrows 1 alpha arrows 1, 2, 3 alpha. What is this? This is axiom 3. I had 2 negations here. I deleted them and reversed the order. So this is axiom 3. So this is axiom 3. Now what am I going to do? Modus ponens. So I can take this guy and delete them, and I'm left with not alpha arrows 1, 2, 3 alpha. Can you see how to proceed now? Yes? I'll use axiom 3 again. I will peel off another pair of negations and reverse the order. So I'll get 1 alpha arrows 1, 2, 3, alpha arrows 1, 2 alpha arrows alpha. This is axiom 3. Again, I'm peeling negation from each of them and reversing the order. What will happen now? Modus ponens. Because I have the head here, and here it is. So I'm left with 1, 2 alpha arrows alpha. Now, this is what I wanted to prove, but I'm not done yet. You see? Right? This is what we wanted to prove. This is what we wanted to prove. But we're not done yet. Why are we not done yet? Yes?
Because we changed it so we have to now prove.
Right.
We have to get A this time.
Because now I need to prove something different. Now I need to prove just alpha from the assumptions. Okay, but I have these assumptions, so how will I prove alpha? Again, so I'll write not alpha assumption, and I'll do modus ponens, and I get alpha. So what I ended up with, a proof of alpha from these assumptions, which by deduction gives me a proof without anything of not alpha arrows alpha. So deduction really makes our lives a lot easier, and it was not so difficult to prove. Okay. So I paid my debt to you, and we have time for a little bit more important notions. We are, except for the soundness theorem, this lecture is all about syntax. So another very important syntactic notion, another important, very important syntactic notion is consistency. So what does it mean that a set of assumptions is consistent? So here I have a definition. Sigma is consistent if anybody wants to propose, how will you define a set of assumptions which is consistent? Yes?
Such that it can't logically imply alpha and not alpha?
Very good. Okay. So if for no alpha, sigma proves alpha, and sigma proves not alpha. It will never prove a statement and its negation. Well, it's kind of what we expect. Something is consistent if you don't, it doesn't imply conclusion and the opposite of the conclusion, right? But there is something unsatisfying about this definition. Because we are now living in the syntactic world. And in the syntactic world, why should I care so much about this square, how do you call it, right angle? This is just a symbol. Why does this symbol play a special role? You see, this is a good definition from a semantic point of view. But from a syntactic point of view, somehow, why do I hate this symbol? Why this symbol, not other? So here is an equivalent statement which is cleaner from the point of view of syntactic. So let's call this definition 1. Let's give definition 2. Sigma is consistent if there exists some alpha such that sigma cannot prove alpha. So this is very clean. Something is consistent, or in other words, it's inconsistent if we can prove everything. Now, this is nicer because there is no special role to any symbol. This is completely just playing a fair game. Now, of course, we'll have a claim. The two definitions are equivalent. So we started with the intuitive definition, then we came up with a more elegant definition, but we claim that they are equivalent. And what shall we do now? Say goodbye and have the proof on Thursday. Thank you.